Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing our examination of amines, specifically the reactions of amines. Having in the previous scribblecast lecture established and examined the basicity of amines, we're going to move on and look at a wide assortment of reactions that amines can undergo. Now, one of the first reactions we're going to look at, of course, is nucleophilic substitution of alkyl halides. And this reaction was covered in the preparation of amines. The reason it's covered in both areas is that amine is both used, both being prepared, can be prepared by this, but it's also involved in the reaction. For example, I can take a molecule like methylamine, and if I take CH3NH2, we have ethyl chloride. The CH3NH2 molecule is a powerful nucleophile, and being a primary alkyl halide, we can get an SN2 attack, and that will produce, all right, initially we will get CH3 NH CH2CH3 positive. Initially we'll get the cation, but the presence of excess base will deprotonate this, giving us a new amine, kicking out chloride. Now, the presence of the nucleophile amine is also the presence of a powerful base. Now, this is less problematic for primary alkyl halides because if it acted as base producing alkene, you get an unsubstituted alkene. And that would mean you'd need a significant amount of heat to favor that. But you're going to get some alkene impurity. This impurity becomes a problem as you put more substitution on the alkyl halide. Going to a tertiary alkyl halide will give you such a substituted alkene that it may compete significantly and produce alkene rather than the desired amine. Now, one of the problems with this reaction, of course, is that it can continue. We can attack again. CH3CH2Cl, nucleophilic attack, primary. We'll get a methyl. Again, initially it will have a proton, but that proton can be taken off, so we'll have a CH2, CH3, CH2, CH3, and our lone pair. Now, one last thing is that it can happen again. And note the base is becoming more and more substituted, so it becomes a poor nucleophile. However, with the primary, you may get reaction. It'll be slower to react, but it could react. And we get this triethyl methyl ammonium cation. And since the alkyl halide was a chloride, we'd have chloride as the counter ion. Synthetically, not very useful because you get such a mixture of products. Now, amines can also be synthesized and prepared. So it's a reaction by reaction of amines with acid chlorides. You may recall that if we take acid chloride from the carboxylic acid derivative section, react it with methylamine, we will produce a protonated amide. We'll get nucleophilic attack, kick out the chloride, nucleophilic acyl substitution. And the protonated amine that forms, so again we get an NHCH3, which has a H here, so the N's positive. It very quickly gets deprotonated by base. Base will come in and grab the proton. That'll form the methyl ammonium salt. So CH3NH2 will come up and pick up a proton. It will form CH3NH3+. It grabs the proton. And then you get the amide. Well, amide's not an amine, but we learned that if you take an amide with one lithium aluminum hydride in ether and 2 H2O, we can reduce an amide to produce an amine. So this was also a preparation of an amine, but because the amine is attacking the acid chloride, it's a reaction of a methylamine. So one amine used to produce a new one. And we examined the reaction mechanism of this amide reaction in the carboxylic acid derivative section. A very useful reaction is referred to as the Hinsberg test. And while it doesn't proceed the same way, the Hinsberg test is to amines, what the Lucas test is to alcohols. Now, if you remember, the Lucas test was simply a test where you add Lucas reagent to an aqueous solution of your alcohol, and depending how fast the precipitate forms, you could determine whether you had primary, secondary, or tertiary alcohol. Well, the Hinsberg test is somewhat similar in determining whether you have a primary, secondary, or tertiary amine. It is a reaction with benzene sulfonyl chloride. Benzene sulfonyl chloride. In this reaction, we take benzene sulfonyl chloride we take H2NR. So suppose we have a primary amine. We react it in base. And the reaction produce what is called a benzene sulfonamide. If you like, benzene sulfonamides are like amides, but instead of carboxylic acid base, they're based on the sulfonic acid. So instead of a C double bond O, you have this S with two double bond O's. And just like in an amide where you have a C double bond O and then an N, you have an HR form. So this is a benzene sulfonamide. If you react with a secondary amine, where there are 2 carbons off the amine, do the same reaction, you get a fully substituted benzene sulfonamide. With 2 R groups on it. The last reaction, of course, is with a tertiary amine. KOH, H2O. Now in this case, we don't get a benzene sulfonamide because one of the steps in forming the sulfonamide is losing a proton off the nitrogen. The problem is NR3 has no protons. So when it comes in and attacks and you kick out the chloride, you're left with this species called NR3+. And in the case of tertiary amines, this is less stable than the sulfonamide derivatives. So there you have it. In this case, we're using a primary amine. In this case, a secondary amine. And of course here we're using a tertiary amine. Now what's interesting is how we can use this like a Lucas test. And it turns out that we can evaluate these product solubilities under basic neutral and acidic conditions. If we look at the benzene sulfonamides that form in water, and we compare them, their solubilities, if you like, in acid and base. The first one, the primary, benzene sulfonamide, is not soluble in acid, but it is soluble in base. The secondary is insoluble in both solutions. And the final one is soluble in acid. The base is questionable, and we'll talk about that one. It can be soluble in certain situations, depending on the solubility of the free amine. So this could be either soluble or insoluble, so I'll put a question mark there. But you see that they're easily extinguished. They're easily distinguished. Only the primary amine, the sulfonamide, soluble in base. In the tertiary amine, it's the only one soluble in acid, and the secondary amine gives a product that's insoluble in both acid and base. And one may want to know why this results. I mean, By doing this test, this simple solubility test, making the benzene sulfonamide, we can determine if we're given an unknown amine, just like in the Lucas test, whether it's primary, secondary, tertiary. But the question is, why do we get these solubility effects? So let's consider first the product of the primary amine, the first benzene sulfonamide, and consider what would happen if we treat it with base. Now the first thing to note is the neutral benzene sulfonamides tend to be water insoluble. So if you have a molecule like this, there's enough organic on it that it is not water soluble. Just like amides though, sulfonamides are not very good bases. They don't get protonated. If you add acid to this, it does not tend to protonate because this lone pair of electrons is delocalized out to the oxygens, resonance stabilized. So we don't really go anywhere. But if we add base, that same resonance stabilization allows the base hydroxide to pull a proton off and become H2O. If you produce this, you will get this guy. NR minus. And that lone pair can be delocalized out to the oxygens. So I could go this way. Or and so you see that we produce a resonance stabilized anion, and because of the anionic nature, the increased polarity of the molecule, once it's deprotonated, it becomes water soluble. So, if you like, when you throw an acid on the original benzene sulfonamide, you get no reaction. The equilibrium shifted heavily to the right because the lone pair is tied up in resonance. They can't get protonated. This guy is water insoluble. So in acid, the benzene sulfonamide is water insoluble because it stays neutral. It doesn't get protonated. But in base, it becomes water soluble because it becomes this resonance stabilized anion. So this one was water soluble in base, but insoluble in acid. Now what happens if I put an R group here? Well, nothing changes with regards to the acid. I stay water insoluble. But notice there's no proton on the nitrogen to pull off, so I can't in base deprotonate. So it stays in this form, which is water insoluble. So when you have a secondary amine where there's no proton on nitrogen, both in base and acid, it stays water insoluble. Okay. Well, what's the difference when we have, instead of primary or secondary producing benzene sulfonamides, we have this cationic molecule that's not quite a benzene sulfonamide. That is the tertiary amine. Well, let's draw it over here. A tertiary amine has come in and added benzene sulfonyl chloride, and it can't be deprotonated because it has 3 R groups. You can't lose a proton, so it's positively charged. The problem with this molecule is it is a very good leaving group. And so if you react it in water and acid, water and acid nucleophilically attacks, okay? And this NR3+, because it's a good leaving group, gets kicked out. And the OH makes benzene sulfonic acid. Now, benzene sulfonic acid is water soluble. And you will get HNR3+. Now, ammonium salts tend to be water soluble as well. So in acid, the tertiaries are water soluble. And it's the only one that's water soluble in acid. What happens in base? Well, in base, hydroxide and water, the same nucleophilic attack of water will occur, giving you the SO minus, the S double bond will reform, and the good leaving group will kick out. But in base this time, you get benzene sulfonate, anion, because they're under base conditions, and the acid deprotonates. And the amine will exist as the free amine. Now this is where the question mark arose. You may recall in the table I said, well, it depends. You might get it soluble, you might get it insoluble. It depends on this amine. If the R groups are small, like methyls, the amine will be water soluble. And so everything will look water soluble because the benzene sulfonate definitely is water soluble. However, if this amine is got larger R groups, like butyl groups off of it or something, the longer carbon chain, you can make the amine insoluble, so that's not water soluble. In that case, it will look insoluble. So it really depends on the nature of the NR+. Now this really doesn't interfere with the test, because the test, it distinguishes itself by what it does in the acid. Okay. The fact that it's soluble in water in acid, and even long carbon chain species, because it forms a cation, will be more water soluble in acid. Because it's water soluble in acid, it stands out. It's the only one that is. So the Hinsberg test works out really nicely. Again, let's summarize. If we have an H here, okay, we're soluble in base. If there's 2 R groups, right, we're not soluble in either acid or base. And if it's a tertiary, where you get this NR+ unit, you're water soluble only in acid. And so you can distinguish between the primary, secondary, and tertiary amines by how their sulfonamides behave. Okay. Now, what we want to do next is take a look or go back in time to some aldehyde and ketone chemistry and talk about reductions in these situations that can lead to the formation of amine. They tend also to be reactions of amines. We learned that aldehydes and ketones can react with primary amines given a very narrow pH window. If I take methylamine, a pH 4 to 5, I can react to make benzaldehyde methylamine. So I can actually carry out a reaction with amine to produce imine. Subsequently, imines can be reduced with nickel, hydrogen, and of course I could use heat as necessary or pressure, and I will produce a new amine. And if I get this new amine, I get a CH2, NH, CH3. Now, the process of the formation of the imine involves nucleophilic attack of the, and I'm going to just use RNH2, upon the aldehyde. Now remember, aldehydes undergo nucleophilic acyl addition. And so when I'm done this attack, I get an intermediate which looks like this. We have NHHR positive. We have an H off this. Now we can lose H plus. We now have a lone pair here. And let's move this molecule up if we can. Some more room. There we go. Okay, and we can add a proton now. Note the pH is slightly acidic to allow for the addition of protons. That's why I'm adding H+, even though there's amine around. Lone pair here. 2 lone pairs. And we can add another plus H+. Which gives me an OH, H. Lone pair positive. And we have the NHR. Now we have the good leaving group water. We can lose water. Minus H2O. And that gives me a carbocation. CH positive. NHR. I can dump the lone pair in and resonance stabilize this with the nitrogen, producing a iminium ion. Putting the positive on the nitrogen. And of course the last step, minus H+. Deprotonates the iminium ion, giving me my imine. So imines can be prepared by reactions with amines. We've seen that in the aldehydes section of the notes, and we've looked at this mechanism. Note going backwards, let's use a different color for that. Going backwards, I would put plus H+, okay, then plus H2O, minus H+, minus H+, plus H+. Okay. So there's the formation of imine. Imine can subsequently be reduced to make a new amine, as shown in the last step. So imine and, if you like, reduction of imines. Imine formation is a reaction of an amine, and subsequent reduction of the amine can produce amines. Let's modify the aldehyde we're going to look at. I'm going to put a CH3 here. And let's follow this reaction if we put a CH3 there. Again, it's the same thing. Here we go. CH3. Now, before we leave this and explain why I put the CH3s on, let's take a look at the conditions or the requirements for a pH of 4 to 5. pH 4 to 5 is quite acidic, and that acidity is required for the formation of this unit. You see, we need protons to be able to protonate the oxygen so that we can kick out water to make the iminium ion. Protonating the oxygen makes the good leaving group HOH+. If we didn't get HOH+, we couldn't kick out water. And if we couldn't kick out water, the reaction would stop here. And so we needed acidic to protonate. One could argue, then why not just throw in lots of acid? Too much acid would protonate the lone pair on the amine. So likewise, this step right here requires the pH 4 to 5, but for the opposite reason. This step needs the acid. But this step needs it basic. Too much acid will protonate the lone pair. If that lone pair gets protonated, it can't nucleophilically attack. So there's a narrow window. A narrow window which optimizes both conditions. In other words, how low can we take the pH so that we can get the water to leave, but it's not so low that we protonate the amine and kill the reaction. And that turns out to be, in this case, a window of pH 4 to 5. Okay, now let's take a look at the same mechanism and see what happens if I put the methyl group on and try to do this reaction with a secondary amine. Okay, well, what happens is that we don't form imine if we change this to a CH3 twice NH. A secondary amine is used. If we change that, then our amine has two R groups. And it's an NHR twice. And so when we pull the proton off the amine, we now have two R groups. Okay? And everything proceeds the same. And the mechanism can be followed. The amine can attack, we deprotonate, we get this N with two R's on it, then we start protonating the OH, get the water, kick out the water. We've got a resonance stabilized iminium ion, but then we have a problem. This last step. There's no proton on the N to pull off. We can't take off H plus off of the N. This cannot form. So what forms? we pull the plus off instead from the CH2, generating a carbanion. The reason we can deprotonate here is we can move the electrons out on the nitrogen, and when we're done, we end up with a CH2, double bond CH, N, R, R, lone pair. It's resonance stabilized. And what is this molecule? Instead of making an imine, we've made an enamine, an alkene that has an amine off it. So secondary amines give us enamines. The conditions are still the same. You still need a pH of 4 to 5. You still must have it acidic enough to protonate the oxygen, get rid of water, but must be basic enough so that the amine can attack. The only difference is in the very last step where this proton comes off. Where does this proton come off? It can't come off the nitrogen because there's no protons off the nitrogen. That would give you the amine. So instead it takes it off carbon. And because of resonance stabilization, that gives you the enamine. Now enamines likewise can be reduced. Nickel H2 gas can take an enamine to an amine. But there'd be two R groups here. So there you have it. In the reactions of amines, amines can react with aldehydes and ketones to produce either imines or enamines. Primary amines produce imines. Secondary amines produce enamines. Both can be reduced under nickel H2 gas to yield amine. Well, this is partway through a very large reaction section for amines. I think it's a good place to stop. We're going to continue with our look at reactions of amines next Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast. Thank you very much.